Hi there, and welcome to Telefunken. Today's video is one in a series on the vintage Roland CR-78 analog drum machine. In this episode, we take an in-depth look at the power supply in the CR-78. We will be converting the power supply in a machine that was manufactured for the Japanese market, where the domestic supply voltage is 100 volts AC, to one that will be suitable for use here in North America or in Europe, jurisdictions that supply a nominal 120 or 240 volts AC. We'll also be making a few improvements to both the safety and performance of the power supply that could be broadly applicable to some of the vintage instruments in your own personal collection. If that sounds interesting to you, stick around. The schematic for the power supply in the CR-78 can be found on page 13 of the service manual, and the supply itself is on the voice PCB located on the underside of the instrument. The power supply is a relatively straightforward linear supply with no unusual or hard-to-source components other than the power transformer, which we'll describe in some detail in a moment. AC power enters the instrument through a non-polarized connector shown on the left-hand side of the schematic. The line cord is immediately fused before proceeding to a double-pole single-throw switch where both the line and neutral are switched in unison. Across the line lies C400, a 10 nanofarad 400-volt capacitor that acts as an interference filter, preventing reintroduction of noise into the line. Power proceeds from the switch directly to the primary winding of the power transformer, which in our case is a Roland part number 022124N, with the N presumably designating Nippon for the Japanese market. The correct transformer for the CR-78 here in North America is 022124C, the transformer for 120 volt service, and for Europe the correct part is 022124D for the 220 or 240 volt service. Each of these transformers have three independent secondary windings that provide independent AC sources that provide power to the three main DC rails used in the instrument. After passing through independent fuses, each AC source is sent to an integrated full-bridge rectifier converting the AC to DC power. The rectified DC power is then smoothed by 470 or 220 microfarad electrolytic capacitors before being regulated to maintain the target 5, 15, and negative 5 volts. Voltage regulation is accomplished using the Jelly Bean 7805 and 7815 voltage regulators, which further smooth the DC. Both positive and negative 5 volts are regulated by 7805s. In the case of the negative 5 volts, the regulator is a smaller, low-power TO93 package mounted directly to the PCB, while both the positive 5 volt and 15 volt regulators are the more typical TO220 packages, are mounted to the instrument chassis, which acts as a heat sink helping dissipate unused power. The result is that the power supply produces three independent rails of smooth DC power, plus 5, plus 15, and negative 5 volts. The 15 volt supply splits off and passes through a 10 ohm resistor, forming what I'll refer to as a second conditioned 15 volt supply that's used in some of the CR-78 circuits, where it becomes beneficial to provide some isolation from the main 15 volt supply. In this video, we'll describe a number of changes we'll be making to ensure that this instrument continues to operate safely for years to come. The first thing we'll want to do is address the non-polarized power plug, which I believe has some potential to present as a safety hazard. My personal preference is to have all of the audio equipment in my studio properly grounded, so we'll be adding a 3-prong grounded plug that will also ensure that whenever the instrument is plugged in, the hot line will enter the fuse before it goes anywhere else in the instrument. We'll also be replacing C400 with a more modern X2Y2 safety-rated capacitor. Safety capacitors are manufactured in such a way that they're guaranteed not to fail short, unlike the capacitor that's currently in the instrument that does indeed have the potential to fail short, hence the name death capacitor. We'll also need to either modify or replace the power transformer. We'll talk about that more in a minute. The 3-bridge rectifiers will be checked to ensure that the proper voltage drops are present across each terminal, that the rectifiers are functioning as 4 diodes in bridge configuration, and there are no opens, shorts, or failing diodes. All of the electrolytic capacitors in the power supply will be replaced with new capacitors. We'll replace them all as they're more than 40 years old at this point. We'll also be upgrading them slightly. Those of you with a keen eye will notice that the electrolytic capacitors on the 15-volt rail are only rated at 16 volts. That's a little too close for comfort, at least in my book, so we'll increase the voltage ratings in those capacitors to give them a bit more room to breathe and ensure longevity. We'll also make sure the initial smoothing capacitors are rated at 105 degrees Celsius, which will ensure they last a long time. Once we're done with our modifications to the supply, we'll check its performance, first ensuring that we have stable rails and then monitoring each for noise. Spoiler alert, we're going to find that the 5-volt rail is noisier than we might prefer, but there's an easy fix for that. We'll be installing an additional filter capacitor on the 5-volt rail across the output of the voltage regulator. Before we get started, let's talk about that transformer. As we mentioned, the transformer is shown in the schematic as having 3 independent secondary windings. While that in of itself is not unusual, it's common to find transformers with duplicate or center-tapped secondaries that provide 2 windings at 1 voltage and a third secondary providing a second lower voltage. It is somewhat unusual to find in solid-state gear transformers with multiple secondary windings where one winding provides the higher voltage and multiple windings supply a common lower voltage, which is the configuration we have in the CR-78. For this reason, it might be hard to find a suitable replacement transformer for this machine. The reason we're looking for a replacement transformer has to do with the way transformers work. The transformer in the CR-78 is a voltage-reducing transformer that works by passing the line voltage through a primary winding that's wound around a ferrous core. When current flows through the primary winding, it induces a magnetic field, which in turn induces a proportional current through the secondary winding. The relationship between the voltage present across the primary winding and the voltage induced in the secondary winding is determined by the number of turns in each respective winding. Since our transformer is designed for a 100-volt service, if we plug it into a 120-volt outlet, we would expect that it would produce voltages at the secondary windings that would be 20% greater than what the circuit was designed to handle. In addition to stressing the underrated capacitors we've already discussed, our linear voltage regulators would have to dissipate more power to drop their input voltage to their respective targets. While a 20% increase in input voltage might not sound like a lot, if we consider our 15-volt rail for a moment, the rectified, unregulated voltage might be expected to be near 20 volts, and the 7815 regulator will have to dissipate a certain amount of power as heat to regulate that down to 15 volts. If we increase the input voltage by 20%, that provides us with another 4 volts, almost doubling the amount of power that needs to be dissipated by our 7815 to reach 15 volts. A relatively simple solution might be available to us if we can simply modify the power transformer. Since the secondary voltages are determined by the primary voltage and the transformer turns ratio, it might be possible to change the turns ratio by removing windings from the transformer primary until we get to the secondary voltages we're looking for. Although not for the faint of heart, this isn't as crazy as it sounds. Depending on how the transformer is wound, the primary winding might be readily accessible. Unlike the transformers in the previous slides, the transformer in the CR-78 is wound on an EI core, so called because it's comprised of several metal plates, shaped either like the letter E or a letter I, that are assembled around a bobbin upon which the transformer windings are wound. There are different approaches to winding transformers, even those on common EI cores. They can be wound in an overlapping fashion, where the primary and secondary windings are wound on top of one another, sometimes overlapping in alternating layers, or the primary and secondary windings can be wound separately in a split winding. This later approach has considerable safety benefits, as the consequences of a winding failing are generally less severe because the primary and secondary windings never come into physical contact. If the transformer in the CR-78 was wound on a split bobbin, it would be relatively straightforward to modify. Sadly, it is not. Opening the transformer reveals an overlapping concentric core structure that I'm not willing to attempt to modify, so we'll be forced to find an alternative. So the first step in sourcing a replacement is finding out what we're working with to begin with. I've measured the output voltages of the transformer when it was connected to a variac set to 100 volts and the transformer windings were unloaded. The transformer supplies about 20.6 volts AC across the red windings, 10.6 across the orange, and 10.1 across the yellow when unloaded. We can estimate that the loaded voltages will be about 10% less than the loaded voltages. If we wanted to go crazy, we could estimate the exact voltage drop across the transformer when loaded, using Ohm's law and the DC resistance of each winding. But in order to do that, we would need to measure the current draw on each winding, and right now our CR-78 is broken, so we can't do that. So we have a transformer that's producing approximately 18 volts AC across one secondary and 9 volts AC across the two other independent secondary windings. But what do we need? We need to be able to support the 15 volt rail and the plus 5, but what about that negative 5 volt rail? What's it used for anyway? Is it absolutely necessary? If we examine the schematic of the CR-78 very carefully, we can find the negative 5 volt rail on the logic board. The negative 5 volt rail is used in one place and one place only to supply a negative voltage to the 2708 EEPROM. There are two scenarios in which a CR-78 can dispense with a negative 5 volt rail. In one, the 2708 EEPROM is replaced by a compatible chip, such as a 2716, that does not require negative supply. This might require a very minor modification to the circuit around the EEPROM, but nothing we can't handle. The second scenario is one that could apply here as well, as we'll expect to be installing a MIDI kit in this CR-78, and it is possible to dispense with both the EEPROM and RAM chips, assuming we're using the appropriate MIDI kit. Indeed, the Tontec MIDI kit for the CR-78 does not require a negative 5 volt supply, as it combines the CPU, EEPROM, and RAM in a single PIC microcontroller. We'll do a separate video on this kit at some point in the future, and we'll show you how it works, but spoiler alert, it works great. So, since we know we'll be using this kit, we can simplify our transformer search and look for one with only two secondaries. The transformer we'll use is an R-core transformer designed for low noise applications such as precision headphone amplifiers. With dual primary windings, it will work at 120 volts or 240 and has a center tapped secondary providing 15 volts a side and a single secondary providing 9 volts. We'll use one of the 15 volt secondaries to generate our 15 volts DC, and the 9 volt secondary will be used to generate our positive 5 volts. This transformer is rated at 30 volt amps, which is plenty for our application. Before we get started, I wanted to say a few words of caution. In particular, I would like to draw your attention to some errors in the service manual. The illustrations in the manual that show the voice board PCB layout and the power supply incorrectly label the power supply voltages on pins 23 to 28 of the PCB. Some of these mistakes are also present on the actual PCB itself. The service manual contains a list of errata on page 12 or page 34 of the PDF version that show the correct voltages. If you're doing any work on your CR-78, pay attention to this area and make sure you don't hook things up incorrectly. Also, one more cautionary note. Although generally safer than their switch mode counterparts, linear power supplies do contain line level voltages that could be dangerous. Please do not attempt any of this kind of work if you're uncomfortable or don't know what you're doing.
Before rebuilding the power supply, and that will include replacing the transformer with one that's more appropriate for North American voltages, recapping the power supply and recapping the rest of the board upon which the power supply is built, what I wanted to do was get sort of a baseline for the performance of the power supply and see if maybe it's contributed to any faults that we might find subsequently in looking at the CR-78. The way I've oriented it is consistent with the diagrams in the service manual that will show you the PCB layout. And what I've done is I've clipped onto the center lead of the 7805 integrated circuit or voltage regulator, which is regulating the negative 5-volt rail. I've also unplugged all of the connectors on this board and the major connectors on the logic board on the other side. I've also removed the wire wrapped connectors that connect the power supply board, this board, to the logic board on the other side of the instrument. You can't see that. We're plugged into a variac. The variac is set at 100 volts AC and also has a electronic circuit breaker built in. If we have any problems powering this thing up, if it draws too much power, it will shut down within a few cycles and hopefully thereby prevent any damage to this instrument. And without further ado, I will turn on the power. What we see is the 5-volt rail, negative 5-volt rail is producing negative 5.072 volts DC. And in terms of the AC ripple that we're measuring here, it is very modest. It is below 1 millivolt AC ripple, which is absolutely satisfactory. I'll turn this off and reposition. In this case, what I'm going to do is clip onto R600, which is over here next to this purple jumper wire, which carries the plus 5-volt rail. So clipped onto that resistor should be able to read positive 5 volts. And indeed, if I turn the power back on, we see 5.057 volts. And the AC ripple in this case it's actually quite a bit greater than that on the negative rail. It's 9.6 millivolts. It doesn't have a specific periodicity. It's around 7 kilohertz. It looks like noise to me, but nonetheless, we'll see if we can bring that down somewhat by rebuilding the supply. Turn the power off again. Reset the voltmeter to DC. And this time, we're going to look at the positive 15-volt rail. And we can measure it off of either of these two resistors over here. We're clipped on to R529, or actually 523. This is R523. And we should be looking for 15 volts here. What we see is 14.922 volts DC. And the ripple on this 15-volt supply is again below 1 millivolt AC. So that suggests that of the 3 rails, they're all within specifications in terms of the absolute voltage. The plus 15 rail has about 9 millivolts worth of ripple that we can try to address, and we'll see what happens. We'll revisit this after we've done the recapping. In order to get access to the bottom of the board, we have to obviously take it off of the chassis, and to do that I've just unlocked the 4 plastic standoffs and desoldered the power transformer where the power comes in from the transformer secondaries into the power supply section. And that allows us to tip the board up and get access to it. I'm going to give my desoldering gun a whirl here and attempt to do this reasonably elegantly. Now these these capacitors are glued as well as soldered to the board. This one does not want to come out, or rather it's stuck with the glue. So that's one of these capacitors. You can see the glue here. Didn't want to give up the ghost. And very quickly, we can take out our little ESR tester and do a quick ESR test. Power this up. Calibrate it very quickly. Easier said than done. Zero. Okay. And this is a 470 microfarad capacitor, and it is showing an ESR of 0.032, which is great. It's suspicious. It's so good. But that's okay. That's well within specifications. A couple things we don't like about this capacitor though. One of them is that it's very, very old. It could be leaking DC, and it's only rated to 85 degrees Celsius. And we really prefer to have 105 degrees Celsius rated capacitors in our power supplies. So that's one capacitor out, and we'll proceed accordingly. This glue is causing me to have far too long of a dwell time, so I may actually change strategies and work with solder wick. So this capacitor was the filter cap on our 15 volt supply, and again we can very quickly check its ESR. That's very odd. There we go. .1 ohm it says. So again, this would be a very good reading. Another challenging capacitor by virtue of the amount of glue here. Gosh, there we go. This is a 220 microfarad at 16 volts. Yeah. And the last electrolytic in the power supply is down here. And it'll be a lot easier to remove if I just use solder wick. This is attached to a huge ground plane, so it's taking a lot of heat to draw up the solder. But I believe that's probably done it, or at least some of it. There we go. Again, lots and lots of glue. I'm going to spare you some of the details here in that I'm not going to force you to watch me desolder the rest of these capacitors. But one thing I did want to point out is something that I'm not sure if you can see. But for example, this electrolytic capacitor right here, it's a 100 microfarad at 10 volts. It is showing signs of electrolyte leakage. It's got down the negative leg of the capacitor a lot of corrosion. It's that green color is the copper on the leg of the capacitor corroding, and that's not a good thing. Perhaps you can see it with from here, that capacitor right there. And some of the other capacitors on this board are exhibiting similar symptoms. And so they'll all be coming out, all the electrolytics that is, and we'll retest the power supply once that is done. So we've recapped the power supply, replacing the electrolytic capacitors, and we've upgraded the filtering on the 15 volt rail, and we're about to examine the ripple that remains on the plus 5 volt rail after replacing these electrolytic capacitors. And if I turn on the power, we have 5.057 volts DC on the plus 5 volt rail. If we switch over to AC, we see that we have 9.4 millivolts ripple, 9.34 millivolts ripple. So replacing the electrolytics didn't resolve our ripple issue. However, we're about to try something else. There are two empty holes here in the printed circuit board. And if you examine the service manual, you'll see that these holes span, or one of these holes is on the ground plane, another is on the plus 5-volt rail. So if I put an electrolytic capacitor across this is a 470 microfarad at 35 volts. And if I put this across this by inserting its legs in these two holes, I've already checked in that there's solder covering the two holes on the other side. We see that we bring this ripple down to 0.97 millivolts AC, which is what we see on the others. So I'm going to do exactly this. I'm going to put this electrolytic capacitor in the circuit. We'll also examine the other rails while we're here. And I've just turned off the power, connecting to now the plus 15 volt rail via these resistors over here. And come back and turn this to DC. Turn the power back on. We can see we have 14.922 with a ripple of again, less than a millivolt. Turn the power off and reposition the probes. This time going for the negative 5-volt rail. This would be the central lead of the smaller of the two 7805 regulators. And turn the power back on. We have negative 5.073. And again, around 1 millivolt AC ripple, acceptable. So I'll turn the power off, position that electrolytic capacitor. We'll go from there. So first thing we need to do is clear out the solder from these holes, these existing holes. You can see them right here on the circuit board. I'm speculating that Roland originally designed the circuit board to accommodate a capacitor in this location and decided ultimately that they didn't actually need one in order to achieve a stable power supply. And they're probably right, but it's not going to harm us at all to put this additional capacitor in here. And the positive lead goes through this hole and the negative lead goes through this hole so that it can attach to the ground plane. Just the same orientation as the other filter capacitor on the other rail. There we go. Again, latching onto negative lead over here. Positive lead over here. when we turn on the power after soldering in the second capacitor, we see that again we have 5.057 volts, and now our AC ripple is substantially reduced, less than 1 millivolt AC. Perfect. So after recapping the power supply and putting in the new transformer, we want to check the power rails. And so right now we're connected to the ground here and the positive 5-volt rail. And I'll just turn on the meter and turn on the variac. And the variac is set at 120 volts AC, so our local power here. I'll turn on the instrument, and we have 5.057 volts DC on the positive 5-volt rail. And if I take a look at the AC voltage present on that, we can see that we have less than 1 millivolt of AC ripple on that rail, which is a great result. I'll turn it off, reset the meter, and connect to the 15-volt rail, which is accessible through these resistors over here. And so we're connected to the 15-volt rail. Turn the power back on, and we have 14.924 volts DC on that rail. We'll go to the AC reading, and here we see again we have less than 1 millivolt of AC ripple on that rail. So excellent results. I'll actually modulate the input AC voltage just slightly. Maybe it's best to monitor the DC voltage. So I'll turn it up a little bit. That's 127 volts, for example, and you can see that it's very stable. 131 volts, and I'll turn it down. It's 107 volts input, 102, 101 volts input, and you can see again how stable that is, how stable that 15-volt rail is. And that's exactly what we're looking for. And here's just a quick look at the replacement transformer wired up. You can see here it's mounted on an L-shaped aluminum bracket. This is about 3 inches wide, 3 inches tall, and about 1.5 inches deep. There are 2 mounting screws that are used for the old transformer, which are used to secure the bracket, and then 4 screws securing the transformer itself. The transformer is wired in such that it is attached to the switch here. The green lead goes to the hot, the black lead goes to the neutral, and I've replaced the original capacitor, which was not a safety rated capacitor that was spanning the AC line, with a safety rated capacitor. It's an X2Y2. And then the secondary wires go through this penetration here. There's also a screen shield wire, this yellow and green wire that is on this transformer, which has been secured to the ground over here using one of the screws from the original transformer mounting. I used longer screws to mount this bracket, and although the chassis is threaded, I've also doubly secured the bracket with nuts on the other side. So initially these bolts go through the chassis, through the threaded portion of the chassis, and then once they're tight, they're held in place by bolts and Loctite. We'll probably be replacing the power cord as well and bringing in a ground lead, which we'll secure here as well to the chassis, replacing the original 2-connector power cord, which the instrument was supplied with for the Japanese market. I really just prefer to have all the equipment in my studio properly grounded. And so I will be putting a ground on this device to keep the noise down. So the next step, after ensuring that we have a functioning power supply, is to address what's going on with this board and the damage that it has received as a result of the leaking battery. So we need to remove this board, and as you can see here, there are a number of wire wrap terminals, and we'll need to unwind all of these wire wrap connections before we can get the board out of the chassis here. And that's our next step. When replacing the AC power cable on the CR-78 or any other instrument for that matter, we don't take anything for granted because safety is at stake. And in particular, there are many examples where you can find power cables available for sale, usually online, and oftentimes these will have the leads wired incorrectly. On this particular cable, we have the live and the neutral labeled on the plug, and what we're hoping is that the live and the neutral are connected to the appropriately colored wires. And so this is the live, and it should be connected to the black wire, and we'll test that, and indeed it is. It's not connected to the white, nor is it connected to the ground. And similarly, the neutral wire is connected to the white, is not connected to the black, is not connected to the ground. And just for thoroughness, we'll make sure the ground is indeed connected to the ground pin, and indeed we have connectivity there. So now that we've verified that, we can install the cable in the instrument, and all we do is we strip a small amount of insulation away from the cable, insert it through the cable grommet, or gland as it's called sometimes, far enough so that there's some insulation protruding, and protruding through to the point where the cable clamp will be able to clamp down on the wire. Put this extra layer of protection around the cable, like so. This is just physical protection, and then we put the clamp over top of the cable and insert the screws. Going to use a tiny bit of Loctite here. This is just to make sure that the cable's going to stay securely mounted Oops. Actually, this cable's a bit bigger than the other cable, so it does not need this extra clamp. A little bit of Loctite. And that is plenty snug. Now we secure our ground connector. At the same point as the shield for the transformer. So these two are connected together electrically. And as a last check, we want to ensure that the fuse is actually on the hot line. And we see that it is. So the fuse is connected to the hot line and not to the neutral. And that's the way we want this wired. We want the fuse to be the first thing that the power is coming into contact with, the first thing that the power is going to see as it enters the instrument. And that is providing us with the safest situation possible. If there's any problem inside the instrument, the fuse will blow before it causes any damage. And I've got the fuse partially withdrawn so that the heat from the soldering iron doesn't inadvertently blow our fuse. Or otherwise weaken it, for that matter. Okay. There we are. Brand new power cable. And we can reinstall the fuse, and we should be ready to test the instrument.
Well, that's all for this installment in our series of videos on the CR-78. In a future video, we'll revisit the subject of MIDI kits and install one as promised. We'll also be building a whole new logic board, and we'll be calibrating the instrument to make sure it's working as well as it did the day it left the factory. I hope you enjoy this series as much as I did making it, and as always, your comments, feedback, suggestions, and questions are most welcome.